Greetings, everybody. Trying to work out some technical issues here. I think I have it figured out, and I do. So here we go. What we have here is our handout that we're going to have for our test. Should always have it at our beck and call when we need it. And moving on. We studied triglycerides the end of last lecture, which are esters of glycerol. And you can see the glycerol backbone even here has 3 carbons in a row and an oxygen off of each one. That is glycerol right there, except glycerol has been esterified 3 times here. We have a phosphate ester up here. Everything on this page has a phosphate ester. That's why we call these phospholipids. And we have fatty acid esters here. So when you're asked to draw a phospholipid, please make sure that you draw the fatty acids that I indicate from the handout, previous page. It won't be these two, trust me, but it will be one of these. And attach it like we did with our triglycerides last week. And please remember to make sure those 2 esters are at the end and the phosphate ester is on the other end. Don't put the phosphate ester in the middle. That's not how these molecules are assembled in biology. So remember, phosphate esters on the end of the 3-carbon glycerol backbone. If you also make an ester up here with this molecule called ethanolamine, which is a derivative of choline. Ethanolamine will make a ester here with the alcohol of ethanolamine on phosphate here. So phosphodiester here now. Let's write that down. Phosphodiester. Phosphodiester. If it's with ethanolamine, you have just made a molecule that can be found in neural tissues, and it's a primary phospholipid for bacteria as well. Where does choline come from? Well, if you take ethanolamine and do something like we did last test called exhaustive methylation, now in the lab we use a chemical like methyl iodide. In biochemistry, the principal methyl electrophile is called S-adenosyl methionine, also known in some circles as SAM. Some circles call it SAM with an E, so it became SAME. And methionine is one of the amino acids on our handout right here. And we see it over here. It's got an M. These are alphabetical. I hope you've noticed that by now. There's methionine. And what we have here is a new snip going on. If I can figure out how to work it on this screen. Here we go. Got it. Methionine. Have you noticed there's short forms for the amino acids? I'm previewing something we're going to do very shortly anyway. Yeah, we have to be comfortable using the short forms too. And S-adenosyl methionine means there's an adenosyl nucleotide using the adenine base. Adenine base over here. Adenine here. Oh. And here we go. And we have that over here. And you can read about SAM in the first textbook. Understanding Organic Chemistry, Part 1. But we do not have time to go over reading about SAM. It's a multi-purpose biochemical reagent. Here's two of the pieces used to make it. Ribose is another piece. And on the sulfur, it's attached to the ribose. You'll see its structure when you look up SAM. Anyway, a lot of talk about how do you get choline. Well, choline's precursor to acetylcholine. And there's enzymes called esterases. And if they work on, it's called choline. And the esterase will transfer an acetyl group from acetylcholine SH, and it will deliver that acetyl. No, not SH. Acetylcholine A becomes CoA SH. And you can read about this in our Moodle notes here. And that gets transferred to this. I'm sneaking in stuff that's outside of the phospholipid purview here because you're going to see these molecules in your future. It's called acetylcholine, a very, very important neuromuscular neurotransmitter. And if I'm not writing, if I'm not speaking, I can type better. Typing's dubious on the best of days, writing. And that one's an important molecule for transmitting information from your brain to your muscles. So when you're doing this, you're using acetylcholine to say, I want to do this. And it does that. All right. Anyway, choline in this realm, it's just making an ester with the phosphate instead of with a acetyl group. It's with a phosphate, and you've just made a lecithin, very important phospholipids. These are the components of cell membranes. You've seen the phospholipid bilayer, no doubt, in many examples in biology. And it's got some nutrient properties as well. It's in egg yolks. And it's a good emulsifying agent. It does a lot of good things. Now, if you make an ester instead with the amino acid serine, yep, serine found over here as well, SER, right there. And we're going to go steal that one if I can find my snipper. Serine. So when I ask you to draw a phospholipid of serine, and don't freak out when you can't remember the structure of serine, because serine's on the handout. And you'll see it's attached up there. I do have serine up there already, don't I? Look at me. Copying some, well, that's the handout there. Look at that. Alcohol CH2, alpha carbon to a carboxylate. Alcohol CH2, alpha carbon to a carboxylate. There, same molecule. Now, when you do this esterification, you have made an interesting molecule that was discovered in research just in the last 20 years. This kind of molecule is responsible for cell death, also known as apoptosis. And when it moves inside a cell, it's not good news for that cell. It's time for that cell to die. So what do I expect for you on the test? You should be able to draw a phospholipid of one of these three varieties, as you are cautioned up here. And I will tell you which fatty acids to use. And that's it. And then we're going to do another mini segment here. Moving on to a different type of lipid. This is a steroid. This is the skeleton for the largest possible steroid we'll see. It has all the carbons. In the reading, you'll see that every carbon here is made from acetyl-CoA. So acetyl-CoA, C-CoA, provides every carbon of every type of lipid and it uses the acetyl group, the acetyl. So you'll often see that things like fatty acids have multiples of 2 carbons always. There's never an odd number fatty acid. It's because you're always adding 2 carbons. And you'll see that Claisen condensations are involved and hydrogenations and dehydrations as you look through the notes at Moodle, but we do not have time to get into that. You will, on a test, be asked to draw a steroid, and from nothing, from words. So here is an actual test question. You will not have this big old picture here with these numbers on it. You must learn the numbering system. So how do you learn the numbering system? Well, you say, okay, where's 1? We should always start at 1. 1 is on the A ring. So the first thing you do is draw your rings. You might as well get a start on our answer over here. It goes 6 right beside 6. And then you jog up towards another 6, A, B, C, and then a 5 straight off of that. So I just copied the rings as I saw them here. Carbon 1 is off the to the left of the bridgehead here. And then we count 1, 2, 3, 4, 5, and we go around the first 2 rings, all the way around their perimeter, 6, 7, 8, 9, 10. And where do you go for 11? Well, you got to get up to the C ring as close as possible to 10. There, 11, 12, 13. And now it's different for the D ring. You don't go all the way around because you'll be continuing outside the rings very soon. So you go 11, 12, 13, 14, 15, 16, 17. Now, steroids. They have methyl groups that are in blue almost always. Almost always. So you don't have to tell me when a methyl group is present. If I give you a picture of a steroid, which I will also do on the test, these methyls are almost always present. I want to know if they're absent, really. So say the methyl 19 is missing or methyl 18 is missing. That happens. Steroids often stop in this area here. Not all steroids have, not all have this group. There's variations on the group here. It's incredibly rare to see 24-1 and 24-2, but a few steroids do have them. Generally, you won't hear discussion of those. But I hope you see terpene patterns in here because that's how steroids are made. And where else are we going to go from here other than just moving on? Notice that after you get to 17, the rings are done. 18 is the closest methyl to 17 on the bicyclic here. And then 19 is the one down here. And then 21 is the first methyl off of 20. So yeah, 18, 19. Then you come back to numbering 20. That's a normal methyl, so it's 21, 22, 23, 24, 25. That's a normal methyl, so it's 26, and there's 27. And we have that. And here we're going to have alcohols on 4 and 27. There's an alcohol on 4. 20. We better all draw all the way to 27. So we're going to draw 20, 21, 22, 23, 24, 25, 26, and is that 26? I think so. And we have an alcohol on 27. Yeah. And normal methyl groups and 24 prime. So I found one that had 24 prime. I probably hunted hard for that. 24 prime goes here, right there. And there's a ketone on 1. That's ketone. And alkenes between 2 and 3. 2 and 3. As well as 24 to 25. 24, 25. So 20, 22, 23, 24, and 25. And it says there's an epoxide between 5 and 6. 5 and 6 has an epoxide. It's a very interesting steroid here. And carbon 22 has an oxygen. 22 has an oxygen. Okay. And forms a lactone with a carbonyl on 26. Well, that was 27. This is 26. Carbonyl. I mean, you're stretched for time all the time here, right? And life doesn't have to look pretty. Just say carbonyl is attached to that oxygen there, and you're done. Works for me. Doesn't have to look great. That is an alpha, beta, gamma, delta lactone if you're keeping score with what we learned previous. Alpha, beta, gamma, delta. That's the one that closes the ring. That's just a bond. And yeah, points. So get ready for those. And get ready for ones where you're going the other way. I give you the picture of a steroid and you tell me what groups are on what carbon numbers. You'll see examples on the even this fall 18 exam of that. And that is a nice spot for our first break. We will pick up after our question. Yes?
Yes. I think we just forgot to add the 2 methyl groups.
Oh, we forgot to add the 2 methyl groups. The normal methyl groups?
Mm-hmm.
You are correct. So yeah, normal methyl groups, and you didn't put them on. Shame on you. That's shame on me, right? You're going to put them on. So our normal methyl group 19 is here. And our normal methyl group 18 is here. We already took care of normal 21, I believe. Yep. And apparently 26 wasn't normal anyway, but based up to the words to here, I wanted you to draw 26 clearly. And then I said, oh, by the way, 26 is a carbonyl. So it started as a methyl and then it became a carbonyl because we were told. And there we go. And thank you very much. I didn't want to leave that loose with mistakes on it. And when we're coming back, we're going to look at proteins. I usually go into a little more detail into lipids. Time's a factor, and I don't want to just cram stuff down your brain. So we're going to just go with the most important stuff. And we're going to have to try to remember why. What's the word that comes to your mind when we talk about protein, physical, and chemical behavior? And I'm just going to cut to the chase before the break. The number one thing that comes into your mind is always shape. So get your biology hats on. We're going to review the factors that tell us what shape a protein has. We're going to look at a teeny protein here and then characterize bigger proteins and move on from there. So I'll see you very soon and see ya.